Здравейте, Ista, как си? And now I have no words in Bulgaria that I know that I can use. No, there is one, I will use it later. So my name is Vlad Khononov, and usually I am associated with that monkey, that me before shaving. And you know what? Who here has already read this book? So we have two hands, you're awesome. The rest of you are awesome as well, but you know what you have to do, right? I don't have to say it aloud. Okay. Anyway, today I'm not going to talk about domain-driven design, but another topic that is near and dear to my heart, and that's software design in general. Now, coincidentally or not, it is also the topic of the book that was published last month. It's called Balancing Coupling in Software Design. Now, when I started working on this project, my friends, my colleagues were asking like, okay, so do you really need 300 pages to say that coupling is bad? Like, what's wrong with you? Are you going to repeat that? Well, that's how coupling is usually perceived, as something bad. Now, once you start digging in, you will find that there are some nuances. There are hidden dimensions that you can balance and achieve different results. And overall, this book, I would say that it's about things that we understand intuitively, rather we think we understand them, but actually we don't. We have hard time defining these things, we have hard time explaining them, and as a result, we have hard time using them effectively. Now, two such things are complexity and modularity. And you know what, I want to ask you, I know that you just had a lunch, so you're in that post-lunch coma phase. So let's do some exercises to wake you up. Who here wants to design complex systems, like truly complex? Okay, we have a few hands. And who here wants to design modular systems? More hands. And who here can say that they have more experience working on complex systems than modular systems? Even more hands. Cool, cool. So, there are books written about complexity and modularity, some of them over 700 pages long. And I have about 30 minutes left. And during those 30 minutes, I want to make sure that you can explain and define what is complexity, what is modularity, and how you can control your design decisions to steer your systems either towards complexity or towards modularity. Complexity, by the way, if you want job security, let's create that big ball of mud. Let's see how to do it. If not, let's see how to make it modular. So, as I said, 35 minutes, Aide. That's the last word in Bulgarian, I know. Okay, both of these terms, complexity and modularity, they are used to describe systems. So first thing, let's start with making sure we're on the same page about what is a system. And the definition I really like comes from this classic book by Donella Meadows, Thinking in Systems. And in this book, Donella said that a system is a bunch of elements or components that are working together to achieve something, to achieve some goal. So overall, a system is components with interactions between them, and once they're in place, we are able to achieve a goal. And according to this definition, systems are everywhere. Like this computer, of course, is a system. Even the chair you're sitting on is a system. It has multiple components, they're interacting with each other, and it has a goal to make you comfortable, but not too much comfortable, because otherwise you'll fall asleep, right? But in our domain of software engineering, where can we encounter systems? Well, pretty much everywhere. Let's say that you are looking at a bunch of microservices working together. So we have components, microservices, we have interactions, the connections between them, they're working together. And they're working together to achieve a goal. That goal is the functionality of that overarching system, a distributed system in this case. Now, what's going to happen if we will zoom in into one of these microservices? Now, what we have is a bunch of modules, packages, namespaces, however you want to call it, these logical boundaries, it depends on the programming language you're using, but the idea is the same. We have those packages or modules. Again, they have to work together. And again, they have a goal, the functionality of that overarching microservice that they have to implement. Let's dig in further. Within a namespace, we can find a bunch of classes or objects. Again, they're working together, they have connections between them, and they have a goal, the functionality of that overarching namespace or package or whatever you call it. Now, within a class, same story. Now what we have is members or methods of that object. Again, they're working together, they are not really isolated, and their goal is to implement the functionality of that object. So as you can see, when we are designing software, we always have to work with systems. No matter what level of abstraction we are on, we are designing systems. Now, up until now, I use the term component. But what makes a system modular? And there's so many misconceptions about it. So please, till the end of the session, let's try to forget the definitions you may know about what's the difference between component and a module. Instead, let's go back in time to 70s when modularity was just introduced to software engineering, and let's see what they meant by modules back then, in that time. And back then, there was a design methodology that was really, really popular. It was called structured design, and in it, that's how they defined what is a module. So first of all, it's, what are the words they're using here? Statements meeting the following criteria. And by statements, what they mean here is basically a piece of code. Some code that meets the following criteria. First of all, it has a functionality. It implements a self-contained functionality, which means you can describe what that code is doing. It has some responsibility. Second, it should have an API, some interface that you can use to execute that functionality, so that other parts of the system will be able to use it. And finally, it should have the potential of being independently compiled. Now, that word potential is the keyword here. It should be a potential. It doesn't have to be necessarily compiled independently. But once the potential is there, we can say that this is a module. Now, going back to the slides I used a few minutes before, if you're looking at a bunch of microservices working together, what we have is each microservice has a functionality, it has an interface, and yeah, it is independently compiled. Fits the definition of a module. Cool. Within that microservice, let's say we're looking at a package, module, namespace, whatever you call it. Again, we have functionality, we have interface, and yeah, we can compile it independently. We can extract it out of that binary. So each namespace can be treated as a module as well. Classes, same story. Even if we go all the way down to methods, I wouldn't say that you should, but you definitely can compile them independently. So even a method of a class can be considered a module. So given that I reuse the same slides that I used before for explaining what are components of a system, am I saying that components and modules are really the same thing? No. Otherwise, I wouldn't ask you. Not the same thing. The difference is in the goal. When we are looking at any system, by that I mean even the chair you're sitting on, for those who are sitting on a chair. By the way, there's lots of empty chairs here for those who are standing. It has a goal. But when we are looking at a modular system, the goal of modularity is to expand the goal not only to what the system has to do today, but to make it easier for us to implement future goals. So if you're building a software system, you have software business requirements that you have to implement. That's great. If you're making it modular, then you're preparing for reasonable requirements that may come in the future. Now, reasonable, of course, is the key word here, because if you have a CRM system, tomorrow turn it into a driver for a printer, that's not a reasonable goal. That's not the goal of modularity. It should be reasonable. It should be reasonable functionality that you may be required to add to that system. Now, because of that, we cannot say that any component of a system is a module, because if we just decompose a system arbitrarily into components, that's not going to result in modularity. It will result in complexity, for sure. In order to achieve modularity, we have to look for something. But before I get to that part, let's make sure we agree on what is complexity, because if you want job security and you want to achieve complexity, let's make sure we understand what that is. If you want to avoid it, then again, we have to make sure we know our enemy. So what is complexity? That's one of my favorite books ever, Scale. Absolutely recommend it. That book shifts your mental model, how you see the world. Anyway, in it, the author talks about complexity as well, and he has this very cute definition. It's something that you know it when you see it. That's totally correct, but again, let's move away from intuitive explanation towards more precise definitions that we can work with. And we can find it in a framework called Cynefin. Cynefin is a tool for making decisions in different situations. It helps you to find the most optimized course of action when you need to make a decision in different situations. That framework defines 4.5 types of different contexts in which you have to make decisions. For example, let's say you are working on a system and you want to change something. And when you apply the change, you know exactly what's going to happen. And that's exactly what happens after that change. That's not complexity. That's rather an obvious or clear system. If, on the other hand, I don't know what's going to happen, but I can ask somebody, maybe I'm looking at something that written in a programming language that I'm not familiar with, let's say Scala. If I make a change, well, may work, may not work, I don't know. But I have a colleague that knows Scala and can help me. Again, that's not complexity. In Cynefin, it's called a complicated domain. You have an external expert that can help you, that will tell you what's going to happen if you make a specific change. Now, finally, let's say that you don't know what's going to happen, what the effects of the change you want to make are going to be. And the only way of finding out what's going to happen is making the change and looking at the system. Like in some big ball of mud projects, you're making a change and then you observe in production what breaks. That's complexity. That's complexity. When you can find that connection between an action and its outcome only in retrospect. If you have to conduct an experiment, that's complexity. Now, that kind of complexity, where can we observe it in software design? And here again, I'm going to reuse the same slides. I'm going to make my life easier. Microservices. Can you observe complexity if you change one microservice and suddenly everything else in the system breaks? Of course. Namespace, of course. You can make a change, and yeah, something will happen, but you don't know what is going to happen. And of course, methods, exactly the same story. So let's differentiate between two types of complexity, local complexity and global. Let's say that I'm here on this level, and if I change one method, I don't know what's going to happen. In this case, that is going to be the global complexity of that system. Something will break, something will stop working among those interconnections between them, between those components. Now, if on the other hand, I go to the higher level of abstraction towards objects, then that complexity will belong to one of the classes. So we'll say that that's the local complexity of that class or object. Okay? So local complexity is the complexity of the code that you are working on. Global complexity is the complexity of some overarching system. We'll get back to it. It's super important that you notice that it depends on your observation, on your point of view, that type of complexity. Cool. So now we have complexity, but what really causes it? Of course, if you design a system, let's say you define your components boundaries arbitrarily, it's going to be complex. So of course, it's a function of the design, but that's only half of the story. The second part of the story is us, because we have our cognitive limits. In the 50s, they conducted experiments to try to measure what our cognitive limits are. They came to the conclusion that it's 7 plus minus 2 units of information that we can think about simultaneously. Same experiment was repeated 50 years later. Now it's 4 plus minus 1. And I think ChatGPT doesn't bring us to an improvement here in another 50 years. So that's the second part of complexity, our own cognitive limits. Whenever we are working on a system that produces that cognitive overload, if it passes our ability, then we are going to call it a complex system. Then we won't be able to predict what the outcome of a change is going to be. Then we'll have to conduct those experiments or just be surprised after we deploy something to production. So that's the goal of modularity. What we want to do is to design a system, by that I mean components, boundaries, and the way they interact with each other in such a way that will support future goals, future changes that we want to make, and it will help us to manage the cognitive load so that we won't meet that threshold and that system won't become complex. How do we do it? Well, as you might have guessed, it probably has to do something with coupling, right? So let's say we have two components. I'm not telling you what these components are. It doesn't matter. It can be services, microservices, objects, namespaces, whatever. Any two pieces of code that are interacting within a software system. That line between them, it symbolizes that they are integrated. They have to work together. Now, of course, if we imagine that that line is a pipe, through that pipe we can observe some data flowing. One component can say to another one, hey, give me some information. That data will flow through that pipe, or it can instruct another component to do something. Here's the command I want you to execute. Again, that's data. But that's not the most interesting thing. There's something else here, more of, I love to call it in the energy. Whenever we have two components that are integrated in the same system, we have something else that is being exchanged across those two components. And I'm going to be that annoying speaker that asks you what it is. Give me some ideas. Contract. You are very close. We'll get to it. What else? Come on, you knew it. That's cheating, man. Yes, that's knowledge. Because if I want to interact with some component, I need to know some things about it. I need to know what is the functionality of that component, right? I need to know how its interface works. How can I instruct it to do something? In what format or in what way will I get the results? So we have that knowledge that is being exchanged across any two components that are integrated in any system, no matter what level of abstraction we are looking at it. Even if it's two systems that belong to different companies, still they have to exchange some knowledge. Now, we need a way to evaluate that knowledge. But how can we measure it? We cannot measure knowledge. We don't even have those units in which we are going to evaluate it. Instead, let's differentiate between 4 types of knowledges. And each type shares a considerable amount of knowledge, more than the one below it. So this is the model that I called integration strength. By the way, if you remember the book I showed, Structured Design, it is based on that book, just more adapted to our current technologies. I bet you don't want to work with terminology that is based on Fortran and COBOL because it will make you sound smart, by the way. No one will understand what you want, but it definitely will make you sound smart. So anyway, I try to adapt it to make it easier to understand. So first of all, intrusive coupling. We all know that with microservices, all integration should take place through public interfaces, right? I should never go to another microservices database directly and take some data or maybe modify some data. I have to do it through the dedicated public interface. Guess what? Let's say that I want to do it. If I'm doing that, what I'm introducing is intrusive coupling. I'm introducing a dependency on implementation details of that component. Whenever something changes in that component, it has the potential of breaking the integration and resulting in a failure of the whole system, and that's what we call complexity. So that's intrusive coupling. Here we have to assume that all knowledge about how the second component is implemented is shared with the consumer. Lower on the scale is functional coupling. And here, let's say that we have two components that are implementing closely related business functionalities, which means there are use cases that are closely related and they're implemented in those two components. The practical implication is once there is a change in the business requirements of one of those use cases, both components are extremely likely to have to be changed simultaneously. They will have to change together. So again, that shares quite a lot of knowledge about the components. It doesn't necessarily share how it is implemented, but it shares what is implemented in that component. So any change in the requirements is going to be reflected in the second component as well. The extreme example of functional coupling would be, let's say we have two components that are even not integrated with each other in any way, not aware of each other, but they have to implement the same business rule. And if that business rule is implemented in different ways in those two components, the system will end up in an inconsistent state. So we have that, let's call it wireless functional coupling. So again, if previous level intrusive coupling is about how components are implemented, this one is more about what is being implemented by the components. Next one is model coupling. Now, we are software engineers. We love implementing software, but we have to work for business domains that have nothing to do with software. For example, you might be working for a financial company or a medical company. When you're implementing a medical system, they don't expect you to gain all the knowledge about the medical domain. It's not possible. You cannot become a doctor to implement a system. Instead, in the software, what you're doing is you're building a model of that domain, of that medical domain, a model that focuses only on the things that are really relevant to the system you're building, to the problem that you want to solve with your system. Now, if you have two components that are based on the same model of the business domain, that we have that knowledge of the model that is being exchanged across their boundaries. Practical implication, again, if you want to change the model, you have to change them simultaneously. And the higher the complexity of the business domain you are working on, the more you're going to be prone to such changes. So you want to make sure that once you get an insight how to represent the business domain in your system in a better way, in a more efficient way, you have to apply those insights and improve your code base. Model coupling can prevent you from doing that. Now, you said contract. Let's talk about contracts. And finally, we can share a knowledge of an integration contract. Integration contract encapsulates all the knowledge about how the component is implemented, its implementation details. It encapsulates its functional requirements and the models that are being used internally in the component. Instead, it exposes an integration contract. We can say that it's a model of a model. It's a much more stable integration interface that can allow the implementation model to change without necessarily causing changes in the integration contract as well. Once you have that integration contract in place, then you have more freedom to change one of the components without being afraid of cascading changes in the rest of the system. Now, if you will read the book about domain-driven design, then you will find some patterns how to design such integration contracts. Anti-corruption layer, open host service, it's all in domain-driven design. Anyway, these are the 4 levels of integration strength. The higher we go on that scale, the higher the strength of the connection, and the more knowledge we are sharing across the boundaries of the components. Now, knowledge is very important, but that's not the whole story. We also have the dimension of space, the physical distance between connected components. And the thing is, we can observe coupling between methods within the same object, and their implementation is very likely to reside in the same file, right? So that's one end of the spectrum. Another one is, let's say we have coupling across multiple systems. We are on a much higher level of abstraction. Now we have different code bases, different repositories, different projects, maybe even different teams working on those systems. So we have a much larger physical distance between the implementation, the source code of those systems. Why is it important? What do you think? What that red line represents here? What grows as we are going on a higher level of abstraction? What do you think? Complexity. We'll get to it in a few slides, but not yet. There is something else. What else? Sorry? Yes, exactly. Effort. The effort you need to invest to make a change. If you have to modify 2 methods that are practically in the same file, come on, that's going to be easy. You can do it easily. When you have to work on multiple microservices, suddenly you have different life cycles. Suddenly it requires much more effort, more coordination effort, more collaboration efforts. So overall, we can say that the cost of making a change that affects multiple coupled components is proportional to the distance between them. The closer they are, the easier it is to implement the change. The farther they are, well, the more pain you're going to go through. So now that we have these 2 dimensions, integration strength and distance, let's combine them. Now, for simplicity, I will use only extreme values of the 2 dimensions. Let's start with that box. Low integration strength and high distance. What do we have here? Sorry? Bugs? We'll get there. So we have high distance. That means that if those 2 components have to change together, it's not going to be fun. You will need to invest lots of efforts into making that change. However, we have low integration strength. We are minimizing the knowledge that we are sharing across their boundaries, which means we are minimizing the chances of such cascading changes from happening. So we're kind of okay here. That's a combination we usually call loose coupling. Now, what about the opposite? Let's say we have high integration strength, which means we are sharing lots of knowledge. And here what I mean is not sharing that knowledge accidentally because you're too lazy to improve your code, but because you have to. Sometimes you have to share knowledge, right? Of course, we want to strive to minimize it as much as possible, but sometimes maybe you're working on components that are implementing closely related business functionalities. You have to share the knowledge. Maybe you need to use the same model of the business domain. Again, you have to share the knowledge. There's no way around it. So we are in that situation. We have a considerable amount of knowledge that is shared, but not accidentally, but because we have to, and we have no other choice. But at the same time, we are minimizing the distance. We have low distance. So, because of high amount of knowledge, we have high amount of cascading changes. On the other hand, when it's going to happen, it's going to be balanced by low distance. We're minimizing the effort we need to invest to implement those changes. So we're good, again. That's what we usually call high cohesion. Now, what about extremes? Let's say we have low amount of knowledge, but the distance is low as well. So we are not sharing much knowledge, but components are close to each other. Is this good or bad? Who thinks it's good? Who thinks it's bad? Who thinks it's good and bad? I don't know. Pulse check. Well, let's see. If we have a system that is composed of two components, who cares? Seriously. But let's say we have a big system, an old-fashioned monolith, where we have unrelated things packaged together. Low distance, unrelated things, low strength. That means when we have to make a change, we have to make our way through those unrelated things to find the component we really need to change. In other words, it increases the cognitive load. In other words, it results in complexity. We can call it local complexity. It's the complexity of the component we are working on. What about the opposite? High amount of knowledge that is being shared across a high distance. Is this good? Is this bad? Come on, I need all of you. Come on, all of you. Raise your hands. That's bad. That's bad. Okay? You are sharing lots of knowledge. You will have lots of cascading changes, and each one of them is going to be so fun to implement, you will start looking for another job. So overall, we have four combinations. We have loose coupling, high cohesion, and we have local complexity, and we have global complexity. Again, local is complexity of one component. Global complexity is complexity of the overarching system. Where do you want to be on this scale? Again, job security, pick the red. Modular systems and optimizing your work-life balance, pick green. Use this wisely. This is like a Jedi mind trick to design big balls of mud. Now, this relationship between the integration strength and distance can be expressed as strength XOR distance gives us modularity. If they're inversely proportional, we have modularity. If they are not, or in other words, they are equal, the distance is high and strength is high as well, or both are low, you get complexity. And let's optimize this a bit more. M, X, or D, or as someone said, it treats like me said, that notation. How to apply it in your day-to-day work? That's what I promised, to give you a tool. So whenever you're working on a system, coupling is everywhere. Whenever you encounter two components that are working together, evaluate what is the type of knowledge that is being exchanged there. If it's high, ask why. Can you lower it? Can you refactor your system to minimize that knowledge? Again, not always you can do it. Sometimes you can, sometimes you can't. So find that minimal knowledge that you have to share and design the system accordingly. Once you have that minimal integration strength, balance the distance. If integration strength is high, lower the distance. If it's low, increase the distance. Again, the goal here is to optimize the cognitive load. If unrelated things are located in the same component, that increases the cognitive load. If you have things that are changing together, but they're located in different projects, that's cognitive load. That's the way you can avoid it, by optimizing the two dimensions. How are we doing? We have 5 more minutes. Cool. So we have few minutes for a wrap-up. So again, system is a bunch of components working together. If we want to design a modular system, then we are looking not only on current goals, but also we want to accommodate future goals. The Khononov framework helps us to identify complexity, or in other words, an outcome of an action can only be identified in retrospect. And finally, we have these two dimensions that we can combine. Sorry. That's a red alert. I'm from Israel, and we have a red alert in my city. Where were I? So modularity is the combination of strength and distance. If they're inversely proportional, you're good. If they're not, if your goal is job security, you're good as well. Anyway, that's the book available right now. In the book, you will find a bit more elaborate discussion about the integration strength model, because there are also degrees for each one of these levels so that you can compare them. If you have two integrations of the same type, then how do you compare them? It's in the book. And in the book, you will also find another dimension. I have 4 more minutes, I can talk about it. And that's the dimension of volatility. So let's say we have two components sharing lots of knowledge across big distance, but they're never going to change. Who cares? You can avoid it. You can ignore that, you will be fine. For example, when you're integrating with a legacy system that is not expected to change. Again, the discussion of volatility dimension is in the book. And I don't know if do we have time for Q&A? Yeah, so if you have questions, let's do it.
If you have questions,
yeah. I have the feeling that very often there is the situation where you have some requirement which changes, which you have no way of isolating just in few modules. For example, a simple example which I can think of is if you have some kind of an online shop. If, for example, you get a requirement that each product should have a new category in it, you will have changes from the database up to the front end.
Yeah.
How is it possible to apply what you just said to such cases?
Yeah, it is possible, of course. Let's say that the component you're working on is a microservice. Then the database you're talking about belongs to that microservice. We're in the same boundary. So it can be encapsulated, that functionality. It can expose an API. It can be consumed by a website that displays that information. Is that necessarily on cases? That's another discussion, whether you need to introduce that integration contract, or maybe you can just make that part of that web interface a part of your microservice, like in the micro frontends pattern. So the answer is yes, and finding those boundaries is hard. And defining those contracts is hard as well. That's why when you start working on a new system, I always advise to keep things simple, to start with, let's call it a modular monolith, to have logical boundaries within it. Learn about that business domain, learn about things that change, how they change, what are the things that tend to change together. Once you're in the modular monolith phase, it's okay to make a mistake, a design mistake, because you can fix it easily. But if you decompose it prematurely into microservices, then you're in a world of pain, and no one is going to readjust the boundaries of microservices. So I always prefer to start with modular monolith, learn about the business domain, learn how the business requirements change, and once you are more confident in your knowledge, then you can refactor the logical boundaries into physical ones. Hope that answers your question.
Guys, unfortunately, we're running out of time, so give a round of applause to Vlad. Thank you very much for this insightful session.
Let's take a selfie, people.